Yeah, welcome to the Flipped Classroom for AP Calc, session 35, section 4.7. Today we're going to talk about trapezoidal rule and Simpson's rule. Up to now we've been using the idea of the sum of the areas of rectangles to estimate the area under a curve. However, we can also use the sum of trapezoidal areas to estimate the area under a curve. If you remember from geometry, we can define the area of a trapezoid as a plus b divided by 2 times h, where a and b are the length of the top and bottom bases of the trapezoid, and h is the height of the trapezoid. Now, imagine that we place these trapezoids on their sides under a curve. And here you go. Okay, so here's a nice curve, some function, and what we've got here drawn are a number of trapezoids, okay? Notice that the height of the trapezoid is really the width of the x subinterval here. And we're assuming that these subintervals are the same length, although they don't necessarily have to be. It's for calculation's sake, it's much simpler. The height of this trapezoid, for example, this first one, the top height would be the function value at x sub 0. The bottom would be the function value at x sub 1. For the second trapezoid, the top base would be the function value at x sub 1, plus the bottom would be the function value at x sub 2, and so on. Okay, so what you get here is if you add up all these areas, you're going to see that this base and this base and this base and this base and this base are actually used twice, because for one trapezoid they're the bottom, and in the next trapezoid to the right they're the top. The two end bases are not used. The two end points, those bases are only used once. Okay, you'll see what I mean on the next slide. So if y0 is the first function value, we take that y0 times 1/2 times the height. Okay. y1 would be the bottom base. The reason there's a 2y1 is because y1 is also the top base for the trapezoid to the right of it, and so on and so on. So the two end values will only be used once, when all the values in between will be used twice. That's why there's a coefficient of 2. Okay. Another way to write this 1/2 h is really b minus a divided by n, where n is the number of subintervals you have, and so that becomes b minus a over 2n. And more commonly, that's the way this is written. Instead of 1/2 h, it's written as b minus a over 2n times this whole sum, which are all the y values, the function values. Here's a sample problem. Okay, let's say the area of a trapezoid, again, is b minus a over 2n times the sum of f of x sub 0 plus 2f of x1 plus 2f of x2 plus 2f of x in minus 1 plus f of x in. Okay, so let's say they want you to estimate the area under the curve x squared from 1 to 2 using n equals 4, in other words, 4 trapezoids. First step, calculate b minus a over 2n. I do that and I get 1/8. Second step, partition the interval AB into 4 equal subintervals and list the x values and the f of x values. If you look at this table, that's what I've done. I'm going from 1 to 2. I know that the width of each subinterval has to be 1/4, so my x values will be 1, 5/4, 6/4, 7/4, and 2. Okay, that gives me 4 different trapezoids. Then I evaluate the function at each of those x values. So the first one would be 1. I convert it to 16 over 16 for calculation's sake. 25/16, where am I getting that? X squared is the function, so 5/4 squared is 25/16. 36/16, 49/16, 4 or 64/16. Over here, what I've done is I said, okay, this is my f of x0. It's just going to be 16 over 16. But this is going to be 2 times 25/16, or 50/16. 2 times 36/16, 72/16. 2 times 49/16, 98/16. The last value doesn't have a coefficient, so it's just 64/16. Add them all up. Okay, here's the trap rule. Okay, add them all up. I get 300 over 16, which reduces to 75 over 4, and then I have to multiply by b minus a, okay, which is 2 minus 1 over 4. Oh, I'm sorry, b minus a, 2 minus 1 over 2n, which would be 8. So that's 1/8. And the answer comes out to be 2.34375. Now, how good's the estimate? Well, we can find out how good the estimate by just doing something as simple as percent error. If you remember from science courses, we'll take the actual value of the integral, which is x squared of dx from 1 to 2 is x cubed over 3. Evaluated at 2 and 1, I get 7/3 or 2.333. Okay? Percent error is the absolute value of the difference of the measured value minus the true value all over the true value. Whoops, sorry. All over the true value times 100 gives me 0.44%. That's not bad. I should tell you that there's another way to estimate and control error. It's really from advanced calculus, and if we have time in class, I'll go over it. But I'm not too worried about it being on the AP test for you. And like I said, it is from uses some principles from advanced calculus. But this is one way to look at the percent error, which tells you how far you are from the actual value. The second thing we're going to talk about is Simpson's rule. Simpson's rule estimates the area under the curve by summing areas under parabolic arcs on the curve in question. Okay, so instead of using trapezoids, we're going to use parabolic arcs. Now, you might think that, intuitively, this might be a more accurate method unless you have a straight line function, because it makes sense that a curve might fit a curve better than a straight line trapezoid. Picture's worth 1,000 words. Okay, so let's say here we have a curve and we fit, these are parabolic arcs underneath the curve that happen to fit very nicely. Delta x here is the same as b minus a over n, and the formula becomes b minus a over 3n, because I will show you that the Simpson's formula, which the derivation of that, again, I think is beyond the scope of this course, but I will do it in class for you, is delta x, okay, delta x being b minus a over n over 3 times y1 plus 4 times y2 plus 2 times y3 plus 4y4 plus 2y5, so on, all the way into the last y, which has no coefficient. So the coefficients go 4, 2, 4 in the middle. First y has no coefficient, last y has no coefficient. Okay? Okay, sample problem. Use Simpson's rule with n equals 4. So again, we're going to have 4 subintervals to approximate the integral of 5x to the 4th from 0 to 2. Step 1, find b minus a over 3n. So we have 2 minus 0 over 3 times 4, which is 2/12, which is 1/6. Step 2, partition the interval into 4 equal subintervals. Step 3, evaluate f of x at the x values and apply Simpson's rule. So in this table, here's my x values. I start at 0. Because b minus a over n is actually 2 over 4, which is 1/2, I'm going to go every 1/2, so my x values going down this column would be 0, 1/2, 1, 3/2, and 2. Here's my function value, 0, 5/16, 5 or 80/16, 405/16, 80 or 1280/16. Okay, Simpson's value. Well, the first one doesn't have a coefficient. Okay, remember the formula, the first one, no coefficient. Second one, the coefficient is 4. There it is, 20/16. Next term, coefficient is 2. Got it, 160/16. 4 again, 405 times 4 is 1620/16. Add them all up. I'm sorry, 2 is 1280/16. Now add them all up. I get 3080/16 times b minus a over 3n, which is 1/16, which gives me a total of 32.0833 as the estimate for the area under the curve using Simpson's rule. We could also do percent error. When I actually do evaluate the interval, I get 32. Percent error gives me a percent error of 0.26%, which was a little bit lower than trapezoid for the same function. In both these methods, you would think that the more higher n is, the closer your estimate to the true value. And that's true. The more finely you divide the interval, the better your estimate's going to be, the less error. Okay? Here's what we would need to practice on. Problems 1 through 16 on pages 403 to 404. Okay? This is our last section in this chapter, and I remind you that your test is coming up Friday of this week. Have a good day. Bye. There will also be a quiz on this. Quiz, so watch the video for